Today we will discuss support vector machines or SVMs, one of the most powerful machine learning algorithms for both classification and regression problems. SVMs are widely used because they can handle high dimensional data, provide strong generalization performance, and effectively model both linear and nonlinear relationships. Support vector machines are supervised machine learning algorithms primarily used for classification problems, although they can also be used and extended to regression problems. The main objective of support vector machine is to find the optimal decision boundary, known as hyperplane, that best separates different classes. This figure illustrates how engineering data such as payment condition or payment information, asphalt mixture properties, concrete characteristics, and traffic data can be used as input. Support vector machine identifies the boundary that maximizes the separation between the two classes. The highlighted points closest to the boundary are called support vectors, and they play a critical role in defining the classification model. Many engineering problems involve complex boundaries, limited data, and high-dimensional data. These characteristics make support vector machine attractive for engineering applications. The figure compares a simple threshold-based rule with support vector machine. A simple rule uses a fixed boundary and often struggles to find or to capture complex relationships within the data. In contrast, support vector machine searches for the optimal decision boundary while maximizing the difference or the margin between classes. To understand SVM, we first need to understand classification. In this example, the data consists of two classes, pass and fail. The middle panel shows that many different lines can separate the two classes. However, not all boundaries are equally effective. Some boundaries are located very close to one class and may poorly perform when a new data record is introduced. The right panel illustrates the support vector machine solution. Rather than choosing any separating line, SVM selects the boundary that maximizes the distance between the classes. This distance is known as the margin. Maximizing the margin generally leads to better generalization and more reliable predictions on unseen data. The hyperplane is the decision boundary used by SVM to separate classes. In this two-dimensional example, the hyperplane is represented by a straight line separating the pass class from the fail class. Any point located above the line belongs to one class, and points below the line belong to the other class. The mathematical form of the hyperplane is shown on the left side of the slide. The coefficients represent feature ways, and the bias term controls the location of the boundary. Although the figure shows a two-dimensional example, the same concept can be applied and can be extended to higher dimensions. In 3 dimensions, the boundary becomes a plane, and in higher dimensions, it becomes a hyperplane. The maximum margin principle is the core idea behind the SVM. The yellow line represents hyperplane, while the dashed lines represent support vectors. SVM searches for the boundary that creates the largest possible distance between the two classes. The highlighted points touching the margin are the support vectors. These points determine where the optimal boundary should be placed. Support vectors are the most important observations in an SVM model. The figure highlights the data points closest to the hyperplane. These observations define the position and orientation of the decision boundary. An important property of SVM is that only the support vectors directly influence the hyperplane. Points located far from the boundary contribute little to determining the final classification rule. Because the model focuses primarily on these critical observations, SVM can be both efficient and effective, particularly for complex engineering problems. This slide compares two versions of SVM. Hard margin SVM assumes that the two classes can be perfectly separated without any errors. While this works well for ideal datasets, real engineering datasets rarely satisfy this assumption. And that is because in engineering datasets, we usually deal with noise, measurement errors, and outliers. Soft margin SVM allows a limited number of observations to violate the margin by permitting small classification errors. The model becomes more flexible and better able to handle real-world data. Many real-world datasets cannot be separated using a straight line. The left panel shows a nonlinear problem where one class surrounds another. In the original space, no straight line can separate these two classes. The kernel trick solves this problem by transforming the data into a high-dimensional space. After transformation, the classes become linearly separable, as illustrated in the right panel. This capability allows SVM to solve highly complex nonlinear classification problems without explicitly computing the high-dimensional coordinates. The kernel trick is one of the most powerful features of SVM. Different kernel functions allow SVM to model different types of decision boundaries. The linear kernel is suitable for relatively simple problems with nearly linear separation. The polynomial kernel creates curved boundaries and can capture moderate nonlinear relationships. The radial basis function, or RBF kernel, is the most commonly used kernel because it can model highly complex nonlinear patterns and generally performs well in many engineering applications. The Sigmoid kernel produces S-shaped boundaries and behaves similarly to certain neural network activation functions. When little is known about the dataset and the structure of the data, the RBF kernel is often the best choice to start with. This slide presents a practical pavement engineering application of SVM. The objective is to classify asphalt mixtures as pass or fail with respect to moisture susceptibility. Input variables include air void content, binder content, wrap content, VMA, VFR, and probably some other parameters. The central figure shows the optimal hyperplane separating mixtures with low moisture susceptibility from mixtures with high moisture susceptibility. The circled observations are the support vectors that define the decision boundary. The workflow begins with collecting mixture properties, followed by model training, identification of the optimal hyperplane, and finally prediction for new mixture. Support vector machines are popular because they offer an excellent balance between accuracy, robustness, and flexibility. One of their biggest strengths is their ability to perform well even when only a limited amount of data is available, um, which is common in engineering applications because experiments are expensive and time consuming. SVMs are also highly effective when dealing with datasets that contain many input variables. Rather than being overwhelmed by high-dimensional data, SVM can efficiently identify the most informative decision boundary. Another advantage is robustness to overfitting. By maximizing the margin between classes, SVM often generalizes well to unseen data. Although SVM is a powerful algorithm, it is not without limitations. One challenge is that model performance depends heavily on hyperparameter tuning. Parameters such as C, gamma, and kernel type must be selected carefully to achieve optimal performance. Another limitation is kernel selection. Different kernels produce different decision boundaries, and determining the most appropriate kernel is often problem specific. Poor kernel selection can significantly reduce predictive accuracy. SVMs can also become computationally expensive when applied to very large datasets because training complexity increases with the number of observations. And finally, SVM is often considered a black box model because it provides limited insight into how predictions are made compared with more interpretable approaches such as decision trees. This slide demonstrates how easy it is to implement an SVM classifier using Python and scikit-learn. The workflow consists of four main steps: loading the data, training the model, generating predictions, and evaluating performance. The code uses a SVC class from scikit-learn with an RBF kernel, which is one of the most widely used kernel functions. The parameter C controls the trade-off between maximizing the margin and minimizing classification errors. After defining the model, the fit function trains it using the training dataset. The predict function is then used to classify new observations. Finally, model performance can be evaluated using metrics such as accuracy, precision, recall, and F1 score. An important practical consideration is feature scaling. Because SVM is distance-based, variables should generally be standardized before training. In most engineering problems and in most engineering applications, the RBF kernel serves as an excellent starting point. Support vector regression extends the principle of SVM from classification problems to continuous prediction problems. Instead of assigning observations to classes, SVR predicts numerical values. The central concept in SVR is the epsilon-intensive tube. Rather than attempting to fit every data point exactly, SVR allows prediction errors that fall within a predefined tolerance region. Errors inside this tube are ignored, while larger deviations are penalized. The figure illustrates how SVR identifies a regression function that balances prediction accuracy and model simplicity. Only observations outside the epsilon tube become support vectors and influence the final model. SVR is commonly used to predict engineering properties such as dynamic modulus, tensile strength ratio, compressive strength, rot depths, carbonation depths, so on and so forth. Many engineering problems require prediction of continuous variables rather than classification. SVR is particularly valuable because it can model complex nonlinear relationships while maintaining strong generalization performance. The workflow begins with input features, followed by training an SVR model. This model learns the relationship between the inputs and outputs, and then the trained model predicts continuous values for new observations. The examples shown on this slide include TSR prediction, dynamic modulus prediction, and other parameters, other engineering parameters. SVR performance is heavily influenced by 4 key hyperparameters. The parameter C controls the penalty assigned to prediction errors. Larger values force the model to fit the data more closely, while smaller values allow more flexibility. The parameter epsilon determines the width of the epsilon intensive tube. Larger epsilon values ignore more errors and typically produce simpler models. The kernel function defines how input variables are transformed. Common choices include linear, polynomial, RBF, and sigmoid. The parameter gamma controls the influence of individual training samples when nonlinear kernels are used. High gamma values create highly localized decision boundaries, while low gamma values produce smoother models. Proper tuning of these hyperparameters is critical for achieving optimal performance. Although SVM and SVR are based on the same mathematical principles, they solve different types of problems. SVM is designed for classification tasks. It predicts categorical outputs such as pass and fail, or good and poor, or moisture susceptible and non-moisture susceptible. The model learns a hyperplane that separates different classes. SVR, on the other hand, predicts continuous numerical values such as tensile strength ratio, compressive strength, carbonation depths. The figure illustrates the difference. SVM produces discrete class labels, whereas SVR produces continuous output based on a regression function and epsilon sensitive tube. This slide summarizes the complete SVM and SVR workflow. The process begins with data collection and preprocessing. The algorithm then identifies the optimal hyperplane or regression function using support vectors and margin maximization principles. For nonlinear problems, kernel functions are used to transform the data into higher dimensional spaces. Predictions are generated for new observations and evaluated using appropriate performance metrics. Finally, the results are used to support engineering decision making.